So today we're going to continue our discussion of inference and optimal control from Wednesday, and we're going to cover something called inverse reinforcement learning. So in today's lecture, here's what we're going to discuss. So far, we talked about reinforcement learning algorithms that try to optimize some reward function. But we didn't really discuss very much about where this reward function comes from. We just sort of assumed that the reward function is provided to you as part of the task definition. Today what we're going to talk about is what happens if we want to learn the reward function from observing an expert and then using reinforcement learning. So there are some cases where actually defining a reward function manually by trying to essentially program it in can be quite difficult, and it's comparatively a lot easier to obtain demonstration data. So we'll talk a little bit about why you might choose to use demonstration data to learn a reward function instead of directly doing behavior cloning, and then optimize that reward function to recover a policy. And to do this, we're going to actually apply the approximate optimality model, not from last week, but from Wednesday, actually. This is just forgot to fix the slide. But now we're going to use it to actually learn the reward rather than recover an approximately optimal policy from a known reward. So the goals for today's lecture will be to understand how the inverse reinforcement learning problem definition, understand how probabilistic models of behavior can be used to derive inverse reinforcement learning algorithms, and understand a few practical inverse reinforcement learning algorithms that we can actually use combined with deep neural network representations. So let's start with a little bit of motivation just to discuss why we might want to think about inverse reinforcement learning algorithms. So a question that we sometimes don't really bother to ask very much when we talk about reinforcement learning is, well, where does the reward function come from? So in homework 3, you guys worked on Q-learning algorithms, including for Atari games, and there the reward function was kind of obvious. Like there's a game, and the game has a score, and that's basically your reward. So there's a very natural notion of a hand-specified reward because it's specified by the people who made the game. But in a lot of realistic situations, the picture is not quite so clear. So in real-world scenarios, rewards might actually be very onerous to specify. We showed an example of this actually in the introductory lecture of the course back in August when I talked about how, well, if you have a robot that needs to pick up a jug of water and pour it into a cup, this is something that a person would have obviously no trouble with. But for the robot, just figuring out whether it has succeeded at the task, much less figuring out how to do the task, actually requires a really complicated perception system just to see like where the liquid in the glass is. And of course, this kind of stuff comes up all the time, especially in domains that involve interacting with people. So if you have an agent that needs to carry out a dialogue, well, what is the objective function for that dialogue? It might be actually something quite complicated that involves social norms and things like that. Situations like autonomous driving, where you have a vehicle that needs to interact with other vehicles in the road, and the objective is some complicated mixture of reaching your destination while obeying the laws, while also obeying unwritten social norms. So in practice, if we want to use kind of standard reinforcement learning approaches to these types of problems, we would design some kind of reward function by hand, but that reward function is really kind of a proxy to what we really want. We don't really know exactly what's the reward function for successfully carrying on a dialogue, for example, for an automated tech support system, but we might throw together some kind of objective that seems like a proxy that gets us roughly the right thing. But this can be an onerous process, and it can also be very vulnerable to reward misspecification, where we actually set up a reward function, we use RL to optimize it, but we don't actually get the behavior that we expected. And in practice, the way this manifests itself is that you end up spending a lot of time actually adjusting your reward function until you get the behavior that you want. So in these kinds of situations, sometimes it can actually be easier to actually obtain example demonstrations. Certainly for driving, you can get people to drive around. For dialogue, you can get them to talk to each other, and so on. So inverse reinforcement learning is something that we can use to infer the reward function from these expert demonstrations without having to program it by hand. So that's what we're going to talk about. So why should we actually go through this reward learning process if we actually have example demonstrations? So our alternative, of course, would be to borrow the ideas from the imitation learning lecture earlier in the course and try to directly mimic the expert's behavior. This works well in some cases, but it has a few disadvantages. So when you're directly mimicking the expert behavior, you're not really trying to figure out why they did what they did. You're simply blindly imitating, kind of aping their motions or actions, which doesn't necessarily capture the salient part of the behavior, because some parts are obviously more important than others. And sometimes actually the expert has slightly different capabilities. So maybe they have a slightly different embodiment. Maybe they can do certain things that your agent cannot and vice versa. If you can recover their goal, then the agent can optimize that goal with its own capabilities and might actually end up doing the task differently, but achieving the same outcome. And the other kind of part of the reason here is that if we do this right, then our agent actually reasons about what the expert is trying to achieve rather than necessarily what they actually achieved. Especially in stochastic environments, this can be very important. Just because someone obtained a particular outcome doesn't mean that was the outcome they were trying to go for. Maybe it was just random chance. So if we actually reason about the underlying goals and try to figure out what goal they were trying to accomplish, we could, in principle, actually do a better job than they did. This is a video that I actually showed earlier in the course that illustrates this point. This is from an experiment in child psychology. Here, this guy is trying to attempt to do a task, and the child isn't going to imitate this guy because what this guy is doing is kind of silly and not very useful. What the child is going to do is infer their goal and then actually perform that goal using their own capabilities, which in this case are actually greater than the capabilities of the so-called expert. So it would be really nice if we could get our agents to do this kind of thing instead. So the problem of recovering rewards is called inverse reinforcement learning, and sometimes it's also called inverse optimal control. There's actually a long history of research on this topic in optimization and controls that goes under the title of inverse optimal control, going back many decades actually. But its most recent incarnation in the world of reinforcement learning at this point is about 18 years old. So the formulation for the problem is that you're given a definition for an MDP, that means states and actions, just like in regular RL. You're sometimes provided a dynamics model and sometimes not, so you can have both model-based and model-free inverse RL. And you're provided, crucially, with samples that are assumed to come from an optimal or near optimal policy, which I'm going to denote as pi star. I'm going to kind of abuse notation. I'm going to use pi star to denote both optimal and near optimal experts. So near optimal means stochastic optimality as discussed on Wednesday. And then your goal is going to be to use those samples to recover some estimate of the expert's reward function, and once you've recovered that reward function, you can then recover their policy, potentially in new situations or with new embodiments, to actually perform the task. Now, unfortunately, there are quite a few challenges with inverse reinforcement learning. First, inverse reinforcement learning is actually oftentimes ends up being a very underdefined problem. If you see somebody doing something, there are many possible explanations for why they did it. Maybe they did the thing because they wanted to achieve some end goal. Maybe they did the thing because they just like taking those actions. And I'll show an example shortly. Beyond that, it can be very difficult to actually evaluate the learned reward. Like, okay, you just get a reward function. Is it a good reward function for that expert or not? You can get the policy, see what it does, but that question sometimes can be ambiguous without the right models. And also the demonstrations themselves may not be precisely optimal, so you have to deal with noise and suboptimality. But this under definedness problem, this one is really important to understand. Let me show you a little animation. I'm going to show it to you intentionally out of context. So there's this funny world where there's circles and triangles. And I'll just tell you right now, the circle, that's the agent. That's the guy who's trying to do stuff. And the circle goes and does this. Okay. What's the circle trying to do? Any guesses? What is his goal? Yeah.
Match the centers.
Okay, so maybe he's trying to like match the center of the triangle. Any other guess?
Escape red.
Escape red, right? Maybe he just likes going to the direction where the gray arrow points. Maybe he just likes going to the right. Maybe he just likes moving and it actually doesn't matter where he moves and he just happens to have gone right through random chance, right? So there, without any context, there's a myriad of possible explanations, and I omitted the context intentionally because when we observe real people doing stuff, we have a very rich prior about what people like to do. But you have to remember that for the inverse reinforcement learning algorithm, it lacks that prior. All it sees is abstract symbols, changes in state, and it's trying to figure out what the goal is. There's so many possible explanations. So this is actually a very basic and complicated problem in inverse RL. So much of the history of inverse RL research has actually been in proposing models that try to resolve this kind of ambiguity in various ways. So before we discuss how this ambiguity can be resolved, let's kind of formalize the problem a little bit more with symbols. So a little bit more formally, I'm going to write out kind of the formal definition of regular forward RL, which you're all familiar with, and inverse RL, just so that we can see the contrast. So In both forward and inverse RL, we're given the definition for a state space and an action space. We have to know what our states are, we have to know what our actions are. In both cases, we are sometimes given the transition probabilities. So if you're doing model-free RL, then you might not know this thing, but if you're doing something like dynamic programming, then perhaps you do know this thing. So in both cases, you can sometimes have transition probabilities. In regular forward RL, you're given a reward function, R of S comma A, and then you have to learn pi star. In inverse RL, you're given samples that are sampled from pi star. And again, remember that I'm kind of abusing notation, so pi star here might not actually be the perfectly optimal policy, but we assume that it has something to do with the optimal policy, that it's in some sense close to optimal. And then you have to learn the reward, which I'm going to denote as R subscript psi. And the subscript psi denotes that that reward has some parameters, and I'm going to call those parameters psi. So the reward has to be represented in some way. Much of the older work on inverse reinforcement learning employed linear function approximators, meaning that the reward is assumed to be a linear function in some basis f. You can express it also as a dot product, as an inner product between the vector psi and a vector of features f. So these features are basically things that you either want or don't want. So maybe for the car, one feature is the car going fast? Another feature is the car hitting another car? So maybe you want to go fast, but you don't want to hit another car. So then your weights would be like +1 and -1. But you can also use nonlinear function approximators, and we'll actually discuss that today. So you could imagine, for example, that R psi is a neural net that takes in a state and an action and outputs a scalar value, and psi then denotes the weights in this neural net. And then, of course, once you've learned the reward function R psi with inverse RL, then you can use that reward function to recover the expert's policy. So the first topic I'm going to talk about is feature matching and maximum margin algorithms for IRL. I'm going to cover this very briefly because it's not going to be the main topic of today's lecture. Today, most inverse RL algorithms are actually based on the probabilistic formulation that builds off of the material I covered on Wednesday, but many older algorithms are based on maximum margin formulation, so I want to cover those briefly just so all of you have an idea what this is. So one of the earlier attempts to try to resolve the ambiguity in inverse RL went something like this. If you're using a linear reward function, meaning a reward function that is given by the inner product between your weights and some feature vector f, then perhaps one way to resolve the ambiguity in IRL is to say, well, I don't just want to blindly copy all the actions that the expert took, but these features somehow are important. There's a reason someone gave them to me. So perhaps they're not only a good basis for the reward function, but they're also something I can use to compare policies. And maybe I can say that if these features are important, maybe all that really matters is for my learned policy to match the expected values of those features to the expert. So if the expert never collided with another car and always went really fast, so their expected value of fast is big, their expected value of collision is low, perhaps if I match those expectations, I'll recover policies that in some functional or salient way resemble the expert without necessarily having to copy everything. So we can write this out as following. If you let pi superscript R psi be the optimal policy for the reward R psi, what we want is in some sense to pick psi so that pi R psi, so the expectation under pi R psi of our features is equal to the expectation of those features under pi star. So formally, the expectation needs to be under the state action marginals because the features are functions of states and actions. So you take the probability of states and actions, average them over all the time steps, and take the expectation under that. For the expert, of course, you don't know the expert's policy, you just see samples from that policy. So you can approximate the right-hand side of this equation just by averaging together the feature values along the demonstrations. And this gives you an unbiased estimate of the expert's feature expectations. This formulation is better, but it's still ambiguous. Because if you have the features that are not unique, that do not uniquely identify the expert's behavior, you can still have multiple possible explanations. So, you know, if in the example with the triangles, if you have a feature for going right and a feature for going to the purple thing, perhaps you want to match both of those features, but they might not actually both matter. It might be actually only one of the two. But it's a starting point, and we can work with that. And one of the ways in particular that we can reduce the amount of ambiguity in this formulation is instead of just saying we want the features to match, we can say we want them to match and we want the reward for the expert policy to be larger than the reward for any other policy by the largest margin. So that's meant to break ties. So you can have many policies that match the features, but we want to do more than just match the features. We want the resulting reward to have the largest margin against any other policy. That's like saying, pick the reward for which the expert is better than anybody else by as big of a gap as possible, which kind of makes sense. Now, this problem of maximizing the margin, those of you that remember perceptrons and support vector machines will immediately recognize this. Of course, usually we don't want to formulate the problem quite like this because we have these kind of complicated constraints. So we have to do a couple of things. So first, we have to, of course, reformulate the problem in a tractable way. And second, we need to explain what it really means to have a larger reward than any other policy, because there are infinitely many policies and some of them are very similar to each other. So if the expert assigns a probability of 0.9 to some action and another policy assigns a probability of 0.899999, that's a very similar policy, so it's kind of unreasonable to say we want the same margin against everybody. So the other thing we have to do is we have to somehow weight these things by the similarity between pi star and pi, so that your margin against policies that are almost identical isn't considered as heavily as that against policies that are different. So the way that we're going to make this tractable is by basically borrowing an idea from support vector machines, which also perform the same kind of margin maximization. And in support vector machines, we know that we can reformulate this maximum margin problem as an equivalent optimization where we're trying to maximize, or we're trying to minimize the magnitude of the weights while forcing those weights to have a margin of 1, right? So having largest margin versus having smaller weights and fixed margin ends up being the same because there's a scale invariance here. So multiplying psi by a constant over here doesn't really change the behavior, so you can just say let's just minimize it and have the margin be fixed at 1. And then the kind of SVM style formulation of the maximum margin IRL problem also suggests a very natural way to take into account similarity between the policies. Instead of saying that you want a margin of 1 against all other policies, we say we want a margin that depends on some measure of the difference between these policies. So a policy that's very different from pi star, that one is going to demand a larger margin than one that's almost identical. Of course, we have to measure these differences somehow because we don't actually know what pi star is. We only have access to its feature expectations. So then what we might do is we might define the difference in terms of those feature expectations. So say a policy pi needs a bigger margin against pi star if it has very different feature expectations. That's one reasonable way to formulate this margin. So this is a reasonable way to do inverse RL, but there are a few issues with it. First, maximizing the margin kind of makes sense, but it is a bit arbitrary. Simply because the policy has a large margin against other policies doesn't mean that it's in some ways, it's in some sense like a better fit to the expert's actual goal. It's just a way to break the tie, to remove some of that ambiguity, but it's not necessarily removing it in a functionally relevant way. It's just a design choice, essentially. Perhaps more problematically, this approach to IRL doesn't really have a principled probabilistic model of expert suboptimality. So for a perfectly optimal expert, this all makes sense. If the expert is suboptimal, the SVM framework does give you some machinery to compensate for that. For example, you can add slack variables. You can say, well, I'm going to say this is greater than or equal to this thing plus the margin minus a slack variable, and then the slack variable is minimized. But it's a very arbitrary model of suboptimality. It's not really reasoning about why the expert might have made a mistake. It's just saying, we're going to put in slack variables. And the other issue with this approach is that if you have linear reward functions, then these problems are actually very tractable, and there are good SVM solvers that can be used to perform this operation. But if you have a more complex representation of your reward function, such as a deep neural network, it's very difficult to shoehorn this constrained optimization procedure into deep nets. So deep nets would really like to optimize them with stochastic gradient descent for unconstrained optimization. However, if you want to learn more about these types of algorithms, here are some papers you can check out. You can check out this paper by Abeel and Ng called Apprenticeship Learning via Inverse Reinforcement Learning. And there's a follow-up paper by Ratliff et al. Called Maximum Margin Planning that makes the connection to SVMs a little bit more explicit. Okay, so that's it for the margin-based methods, and then the main focus for today's lecture will actually be on probabilistic methods. But does anybody have any questions about this? let's continue. So the way that we can derive inverse RL algorithms that actually do take into account a probabilistic model of expert suboptimality is to build on the ideas that we presented on Wednesday. So on Wednesday we talked about how when you model human behavior, the assumption that the human is actually acting optimally with respect to some reward can be a bit unreasonable because people and animals, they get lazy, they make mistakes, but they don't do so completely arbitrarily. They presumably prioritize the things that are really important to them and are willing to make more mistakes in the places that are less important. And we saw how we could formalize it by representing the behavior as the result of inference in a particular probabilistic graphical model. And this graphical model had some of the parts of an MDP. It had an initial state distribution and a transition distribution. But in addition, it also had these things that we called optimality variables, which are binary random variables whose probability of being true is proportional to the exponential of the reward. And we saw that if we try to infer the distribution over states and actions, conditioned on all of the optimality variables being true, then we obtained kind of a modified reinforcement learning framework that looked just like regular reinforcement learning, except that now the policies were stochastic. And we saw that the resulting objective for the policy corresponds to maximizing reward while also maximizing entropy. And we could plug this into policy gradient, or we could plug this into Q-learning and get back these soft optimal solutions, solutions that favored the optimal behavior, but still had some non-zero probability of executing suboptimal actions based on their expected return. So this seems like a sensible model for how people might perform goal-driven behaviors while making small mistakes in places that are not very salient to their goal. So let's see if we can use this model now to actually learn reward functions, because this model will actually assign non-zero probability even to suboptimal behavior. So just to recap the model, we have transition probabilities. Simply asking the question, what's the probability of a trajectory without any reward doesn't make sense because, of course, that's not taking into account goals. So we introduce optimality variables, and then the inference problem is to figure out the probability of a trajectory given all those optimality variables are true. And in the non-variational case, we saw that if we choose the optimality variables to have the probability proportional to the exponential of the reward, then if we work through Bayes' rule and so on, then we end up with the probability of a trajectory being proportional to the probability of that trajectory happening under the dynamics of the system times the exponential of the total reward of that trajectory. In this lecture, I'm going to work with the simpler model that does not do variational inference, although as you recall from Wednesday, this model actually has some problems in regard to being overly optimistic. And in fact, in practice, when we do IRL, we use the other method. But it's not really going to affect much of the discussion today because all that changes is how you compute the backward messages. So in practice, if you want to actually compute those backward messages, use the variational approach that I described, where your backup looks a lot like the regular Bellman backup. But for the discussion today, I'm going to use this model just because the notation is going to be simpler. Okay, so if you want to learn the reward function, that essentially amounts to learning the distribution over the optimality variables. So the reward function occurs in exactly one place in this model, which is in P of O given S comma A. So now if our reward function has parameter psi, this corresponds to a learning problem in a graphical model. So those are our reward parameters. So now we can write out P of O given S comma A comma psi, just to emphasize that it depends on psi. And the probability of a trajectory given O comma psi, of course, is proportional to the probability of the trajectory happening randomly times the exponential of the total reward. And if we want to optimize this probability for some example trajectory, we just have to compute its derivative with respect to psi. The first term doesn't depend on psi, so if we're doing maximum likelihood learning, all we want to maximize the log probability of this thing. Since the first term doesn't depend on psi, we can just ignore it. So the only term that really matters is this exponential total reward term. If we take the logarithm of the exponential total reward, then our objective just becomes maximize the reward of the demonstrations. Okay, that can't possibly be the whole story, right? If we just say make the reward of the demonstrations big, that can't possibly be a valid algorithm. So there has to be a second term. Does anyone know what the second term is? If I take log probability, where this is my probability, I want to take its gradient with respect to psi, so that first term doesn't matter. What does this objective end up being? Log of exponential reward is r, but there's another term. Any guesses? Anyone want to raise their hand? Notice that this is proportional to, so this is not equality. What is the constant of proportionality?
You're trying to normalize it.
Right, so the answer is you have to normalize this thing, and that's actually where all the trouble comes from. If this was an equality symbol rather than proportionality, then everything would be easy. Then we would just say, let's make the rewards of the demos big. But of course, that makes no sense. If you just make the rewards of the demos big, then the right reward function just outputs huge values everywhere, like it's saying everyone's a winner. But of course, that can't possibly be true. You have to somehow keep the reward big only for what the expert is doing. So the other term that you need to include is to account for the fact that this is a proportionality. So that means that you're maximizing the total reward along all the demos, but then you're also minimizing the log of the normalizer z. This is the partition function. And that's where actually all the difficulties in these inverse RL methods come from, is from calculating that partition function. So this is the hard part. The partition function is basically the integral of the probability of the trajectory over all possible trajectories. So it's the integral of p of tau, this is the probability of the trajectory happening randomly, times the exponential of r of tau. And it makes a lot of sense that you need to subtract this thing, because then you're saying make the reward big for the demos and make it small everywhere else. But of course, there are a lot more everywhere else's than there are demos. So this is a huge integral over all possible trajectories, and it's extremely computationally intractable to compute. Exactly. So we need to do something a little more clever. We can't just sum together all possible trajectories. So what we can do is, well, first we can calculate the gradient of this thing. Let's just use differentiation to compute the gradient of this thing. The gradient of the first term is very easy. It's just the derivative with respect to psi of r psi. And for the second term, from the definition of the derivative of a log, it ends up being 1 over z times the integral of the stuff inside the integral times grad r psi of tau. So this comes from the definition of the derivative of a log, and then the definition of the derivative of an exponential. So now we can look at this thing, the second term, and it actually looks kind of interesting, because we know that this stuff in front of the grad, that's the probability of the trajectory happening under the current reward function, and in fact it's even normalized with the 1 over z out front. So this part is just the probability of the trajectory given the optimality variables and your current estimate of the reward parameter psi. The first part is a sample-based estimate of the gradient of the reward under the expert's policy. So that means that we can rewrite this gradient as the difference between the expectation of grad r under the expert minus the expectation under the optimal policy for the current reward. That makes a lot of sense. It's like saying, well, let's make the reward big for things the expert visits, and let's make it small for things that your current policy is trying to visit. So the first part you estimate using samples from the expert. Those are your demonstrations. And the second part we're going to estimate by calculating the maxent optimal policy for the current reward using the stuff from Wednesday, and then trying to figure out this expectation. So let's talk about that. Let's talk about the second term a bit more. So I'm going to write everything out in terms of time steps now, because this is all at the level of trajectories. So in terms of time steps, this is an expectation under some trajectory distribution of the gradient with respect to psi of the sum over all time steps of r psi. And we can take the sum outside of the expectation, and now our expectation is just with respect to the state action marginals. So you sum over all time steps of the expectation of st comma at under the soft optimal policy for psi of the gradient of the reward at that time step. So let's look at what this this marginal looks like. So the marginal, of course, is given by the product of p of a given s, comma all this stuff, times p of s given all this stuff. And we've actually seen these things before. We saw them on So on Wednesday, we saw how this first term, p of a given s, comma o, is just given by the ratio of the state action backward message and the state backward message. So this was the inference problem number 2 on Wednesday. How do you infer the policy? The second term, P of S given O, this is what we obtained by multiplying the forward and backward messages. So this is the state marginal. So this term we know that's proportional to the product of alpha and beta, the forward message times the backward message. And of course, since we're multiplying them together, here beta is in the denominator, here it's at the top, so the betas cancel out, and you can equivalently write this as the product of the state action backward message and the state forward message. So that means that if you want to figure out this distribution, all you have to do is run the backward pass, which looks like dynamic programming, to calculate the betas, run the forward pass to calculate the alphas, and then multiply them. So backward message times forward message. So now we can think about how we can actually calculate this expectation. We're going to use this symbol mu to denote the product of beta and alpha after we normalize it with respect to S and A. So multiply the betas and alphas, sum them with respect to S and A, and divide by the sum to normalize them. So then this thing becomes the integral of mu times grad R, evaluated at all the states and all the actions. This looks kind of scary because there's 2 integral signs, but actually, if you have a finite number of states and actions, if you have a tabular environment, this can also be equivalently expressed as an inner product between mu, which is now a vector of probabilities of being in every state and action tuple, and this vectorized form of grad R, which is just a matrix where there's an entry for every single state action, and for that entry there's a row that denotes the gradient of R at that state and action. So for countable tabular states and actions, you can actually calculate this. It might be big if there are many states and actions, but it's just a matter of going through all the states and actions and summing together the product of mu at that state and action and grad R psi at that state and action. So for tabular environments, this is quite doable. And it has kind of a natural interpretation. Mu denotes the state action visitation probability for each pair of states and actions, basically the probability that your policy will be in that state taking that action. So from this, we can actually write out the classical maxent inverse RL algorithm, which is an algorithm that we can actually use to learn reward functions in situations where the number of states and actions is small enough for us to be able to sum over all of them. So where we start off with some initialization for psi, which could just be initialized randomly. Then we're going to compute the backward messages, beta, st, at, which we can do using the methods described in the previous lecture on Wednesday. Then we're going to compute the forward message, alpha of st, again, as described in the lecture on Wednesday. Then we're going to compute mu by multiplying them together and normalizing. And then we're going to calculate the gradient with respect to psi. And that gradient has 2 terms. The first term we take by summing together all of our demos. That's from I equals 1 to n. And for each demo, sum over all the time steps in that demo from t equals 1 to capital T. And what we're summing together is the gradient of the reward at the state in action along that demo. So that means make the reward along the demo bigger. And the second term, we're going to sum over all the time steps. And for each time step, we're going to sum over all the states and actions and multiply together the visitation probability times the gradient. And we're going to subtract that. So the states that get visited by the policy, their reward is reduced. The states that are visited by the expert, their reward is increased. And then we just take a step along that gradient. And as we showed in this derivation, this amounts to a maximum likelihood optimization. It's trying to find the psi that maximizes the likelihood of the demonstrations that you saw under this particular model of an approximately optimal policy. And then you just repeat this until convergence. As a quick side note, why is this algorithm called maxent IRL? Well, one of the reasons is, as we saw on Wednesday, this model of soft optimality, the corresponding reinforcement learning objective is to maximize reward and maximize entropy. But you can also interpret this algorithm in the linear case, if your reward is a linear function of some features, as solving a problem where you're trying to maximize the entropy of your policy subject to the constraint that the feature expectations are equal. Which gives you kind of an interesting way to disambiguate things. It's saying, we're still going to match feature expectations, but now we're going to say that the best policy is the one that matches the feature expectations while assuming as little as possible about the rest of the policy. So the policy is as random as it can be, except that the future expectations need to match. In the case of nonlinear function approximators like neural nets, this of course isn't quite as crystal clear, but the same kind of interpretation as far as maximizing reward plus maximizing entropy still holds. Okay, does anyone have any questions about this algorithm? All right, so one of the things I mentioned at this point is that if you're interested in kind of reading about this in more detail, I highly recommend the original paper by Brian Siebart called Maximum Entropy Inverse Reinforcement Learning, which describes the tabular version of this method and describes actually some interesting experiments for learning reward functions in a practical real-world setting. The particular setting that they consider is navigation. So what they do is they collect GPS data from taxi drivers in Pittsburgh, and then they formulate a linear reward function with features corresponding to potential properties of driving preferences, like are you driving on a highway, are you driving on a city street, and so on. And then they learn a reward function to try to explain how the taxi cab drivers actually select their goals, conditioned on their destination. So they collect lots of GPS data and actually end up with some interesting reward functions that exhibit similar statistical properties to the taxi cab drivers. So it's kind of an interesting use case for inverse RL to develop essentially a smart navigation system that takes into account human preferences. Okay, so at this point we're going to take a short 3-minute break, and after the break we'll talk about how to extend these algorithms to high-dimensional and continuous state and action spaces. So we'll be back at 10:48.
About the maxent algorithm, as you're iterating through, does the error, if it works anything like policy iteration, does the error tell you anything about how good your estimate is at that point? Or do you have to wait for convergence?
Well, it's a maximum likelihood method. So it assigns a likelihood to each demonstration, and you can kind of figure out, like if you have 2 different models or something, you can figure out which one is better by which one gets better likelihood, perhaps on a validation set.
Okay.
So in that sense, it's kind of similar to unsupervised learning algorithms. It's you can think of it as essentially density estimation, where the density is represented by a product of dynamics and rewards.
Okay.
Right. So in regular density estimation, if you like fit a Gaussian or something, everything about that density is learned. But here you're saying learn the reward such that a density estimator obtained by multiplying it together with the dynamics gives good densities.
Because I'm trying to think, I've never done IRL. I'm trying to think about, have you picked a big enough feature space? And you have to kind of wait to the end to know that.
Well, yeah, you probably do. So what you can do is you can compare likelihoods on, you would do the same thing that you would do in any other machine learning algorithm, which is you compare likelihoods on validation data.
Yep.
And then you can get both overfitting and underfitting, just as usual. In fact, with inverse RL, overfitting is a huge problem because there's so much redundancy. And then what you would do is you would take your validation data and see what happens there. Another thing you can do is you could just optimize the corresponding policy and see if that policy does what you want in some qualitative sense. Because sometimes if you're doing inverse RL, it's not because you really care about modeling the experts, because you would just want to do the task.
How much performance
Okay.
All right, let's continue. So before the break, I talked about how we can do inverse reinforcement learning in domains where the state and action space is small enough that we can sum together these state action visitations over all possible states and actions. But what about larger problem domains? So maxent_IRL provides us this probabilistic framework for learning reward functions, which seems really appealing. But computing the gradient, as we discussed so far, requires enumerating all the state action visitations, which is only viable for small discrete state and action spaces. And it actually looks a lot like dynamic programming, because if you remember how we compute those backward messages, it's essentially a dynamic programming algorithm with a softmax in place of a hardmax. So if we want to do deep IRL, we'd like to have two additional things. We'd like to be able to handle large and continuous state and action spaces. And second, we'd like to be able to learn even under unknown dynamics. Because if you're going to compute those dynamic programming updates, of course, you need to know the dynamics. So we'd like to do things with samples in order to handle large and continuous spaces, and ideally samples that we can obtain just from running our policy in the environment so that we don't need known dynamics. So next we're going to talk about how we can obtain these two things. So we're going to assume, just like in regular RL, that we don't know the dynamics, but we can sample, meaning that we can actually run trials in the world. And let's recall this equation for the gradient, so the one written out with expectations. The gradient is just the difference between the expectation of grad R under the expert's policy and the expectation of grad R under the policy for the current reward, computed with this maximum entropy objective. So we're going to be estimating the expert using samples because we have to, because all we have from the expert are demonstrations. So if samples are good enough to estimate the first part of that equation, why not use samples to estimate the second half? So why not compute the soft optimal policy for the current reward by running regular RL using any model-free method, and then generate samples from that algorithm to estimate the expectation of the second term. That's actually a perfectly reasonable way to do inverse reinforcement learning, but it has a little bit of a problem. So we're going to use any maxent_RL algorithm to learn this thing. For example, we could do policy gradient. And then we're going to run this policy to sample trajectories and then estimate our gradient with samples. So just to write that out, the first term becomes a sum over all your samples from I equals 1 to n, and these are samples from the expert, so these are demonstrations. And the second term is a sum from j equals 1 to m of these trajectories tau j, which are sampled from the optimal policy for your current reward that you obtain by running your favorite model-free RL algorithm, but adjusting for the entropy. So if it's policy gradient, you add the entropy term. If it's Q-learning, you turn the max into a softmax. Seems good. So any thoughts about what the big problem with this approach might be?
What does it mean to sum over the policy samples? For summing,
so you
iterate through on that?
So you train the policy, the optimal policy with respect to this objective for the current reward, then run that policy m times to collect m samples tau j. It's computationally expensive. Yeah, that's an interesting answer. Let's think about what the computational cost of this really is, right? This calculation gives us the gradient with respect to the reward parameters. We're going to be doing gradient ascent on this. So every time we change our reward, we need to recompute the optimal policy for that reward. If we're computing the optimal policy by running, let's say, Q-learning, and we need, let's say, 1,000 gradient steps to compute our reward function, we essentially need to run Q-learning 1,000 times. And those of you that remember what it was like to do homework 3 might kind of wince at this prospect that you have to now run things not just for 12 hours, but you have to run them for 12 hours 1,000 times. It's a viable algorithm that will work if you have a very fast RL method and you're doing things in simulation, but it's rather costly. So we can do something a little more efficient. What we can do is follow the same basic recipe, but be a little bit lazier about optimizing our policy. So instead of learning P of A given S, comma O, comma psi to convergence, what we can do is not learn it to convergence, but just improve it a little bit. So maybe instead of running Q-learning all the way until you get the optimal policy, you just run like 10 steps of Q-learning. Or you run a couple of steps of policy gradient, or even one step of policy gradient to get a policy that's closer to the one that is optimal for the current reward. Because there's no sense in optimizing the policy, especially early on, when your reward function is so terrible that that the corresponding policy is not going to do anything sensible anyway. So now there's a problem, of course, which is that now your estimator for the second term is biased, because you're supposed to sample from P of A given S comma O comma psi, but you're sampling from some other distribution that is perhaps close to it, but not exactly correct. So you have samples from the wrong distribution, and you need to correct them in order to estimate the expectation under a different distribution. Does anyone have any ideas about how we can do that, how we can use samples from the wrong distribution? Importance sampling, that's right. So that's what we're going to do. We're going to try to figure out the importance weights. And it turns out that actually calculating importance weights here is a lot easier than calculating the corresponding optimal policy. So let's look at how we can use importance sampling. So importance sampling, just to be clear, is going to mean that we have the same thing as we had up there, except that now all these gradients are multiplied by a weight Wj, and we're going to normalize them by the sum of the weights Wj. And the question is, how do we get Wj? So Wj, it turns out, can simply be expressed as the ratio between the probability of the trajectory under the policy on the bottom and the exponential of the reward of that trajectory under the current psi. So let's derive that. The full distribution over trajectories, remember, is given by the product of the initial state times the dynamics times the policy. At the top, we have the probability of the trajectory P of tau given O. So P of tau given O, of course, is given by this thing. So it's the probability, it's just the product of all the CPDs in our graphical model. Initial state, dynamics, and optimality variable. The probability under the policy is given by the stuff at the bottom. Initial state, transitions, and policy. So the initial states are the same, the transition dynamics are the same, which leaves only these two terms. It leaves the ratio between the probabilities of the optimality variables at every time step and the probability of the action under the policy at every time step. Which means that we can express our importance weights as just the exponential of the total reward divided by the product of the probabilities of the actions. Now, there's another question we can ask about this importance sampling procedure, which is that, okay, the way that we get this pi is we're training it with respect to R, but which pi should we use? Which pi is actually going to be best in the end? What is the best pi to use for an importance sampling estimator? You can actually look up in a statistics textbook what's the best distribution to use for importance sampling. It turns out that the best distribution to use for importance sampling for estimating the expectation of some function f is proportional to the absolute value of f times the distribution you want to estimate it under, which makes sense. Like you want to oversample the places where the function that you're estimating is big. So in our case, this means that the optimal pi to sample from is actually the pi that's proportional to the exponential reward. So that coincidentally happens to be the maxent optimal policy for our psi. So if we're using importance sampling and we improve our policy with respect to our psi every single step, we're actually bringing it closer and closer to the ideal importance sampling distribution. Which means that even though these importance weights might be kind of ill-conditioned, they might be very large or very small for bad pi's, we're actually explicitly optimizing pi to make these weights nice. So that's quite an appealing thing. It means that if we're improving our policy successfully with respect to the reward, then we're getting a better and better importance sampling estimator. Better in the sense that it will have lower and lower variance as we improve our policy. So that's good. At this point, does anyone have any questions about this importance sampling derivation? Okay, so this is an algorithm that we can actually instantiate, and we can actually use it to learn reward functions represented by deep neural networks. And if we instantiate this algorithm, we can go through it kind of schematically. So this was the math. Let's go through the kind of the schematic explanation. This is from a paper called Guided Cost Learning. You start off with some initial policy with maybe some random parameters and some example demonstrations, maybe from a person. We're going to sample from that policy, which if we're learning something in the real world, that might mean like run your autonomous car, your robot, your agent, whatever it is, and generate samples from the policy. And then use the samples together with the demonstrations to update your reward function. And the way you update the reward function is you compute the gradient, which is the gradient of the reward averaged over the demos minus the gradient of the reward averaged over the samples, weighted by those importance weights. And then you go back in and you update your pi with that reward function using any reinforcement learning algorithm. And then at the end you get a reward function, and you actually also get a policy that is a policy that is attempting to maximize that reward function. So if your reward function is a good match for the expert's reward, then your policy at the end will also be a good match for the expert's policy. So you actually get both the reward and the policy at the end together. And of course, the improvement for the reward is given by this equation. So let's see this algorithm in action. Let's see kind of what it does. Here is an example evaluation with a robot. This is the process of giving demonstrations. So here, a person actually guides the robot's arm to generate those example trajectories that we're going to use to compute the states at which we maximize the reward. And here the demonstrations are given for a few different positions of this cup. So this person is trying to teach the robot to pour things into a cup. And then the robot has an autonomous learning phase where it trains a policy and generates samples from that policy and updates the reward. And after that reinforcement learning phase, then the robot can go in and try to actually do the task. So now the robot, of course, the challenge in this task is that the robot has to figure out that the position of that yellow cup is what matters for this task rather than the particular motion of the arm. And if this works properly, then the robot should actually pick up on the right objective in the task. Okay, so that's the method. But now some of you might have noticed that this method kind of has the flavor of a game almost. So you have this initial policy. The policy generates samples. And then you have your demonstrations, which are also samples. You can view them as samples from a different policy, from pi star. And your reward function is trying to make the reward of the demonstrations big and the reward of the samples from the policy small. Well, modulo these importance weights. But basically, you need to make the reward from the policy small. So the demos are made more likely and the samples are made less likely. And then the policy goes in and tries to actually kind of do the opposite. The policy tries to go in and change which trajectories it'll generate to generate trajectories that have larger reward. So this thing is trying to make the reward of the policy larger. This thing is trying to make the reward of the policy smaller. And they're kind of competing with each other. And of course, this gradient becomes 0 once the importance weights all go to 1, meaning that the policy is the optimal policy and the distribution matches the expert distribution. Because if these samples come from the same distribution as these samples, then of course when you subtract them in expectation, they come out as 0. So the equilibrium of this game is when the policy matches the expert's policy, which of course has to happen when the reward matches the expert reward. So this idea of trying to match distributions by using a kind of adversarial game is actually something that has been explored quite a bit in deep learning, not in learning from demonstration actually, but in other areas, things like generating images and generating text. And it goes under the name of generative adversarial networks. So many of you have probably heard of generative adversarial networks, but just to make sure we're all on the same page, let me summarize the basic idea. So, okay, qualitatively, the idea is that you can turn horses into zebras, generate very realistic looking faces, and turn line drawings into cats. But the way that you can do all this is by formulating a particular adversarial game where you have one network that's trying to generate data, for example, generate pictures, and another network that's trying to discriminate the generated pictures from real data. So here's the setup. In the first network, which is typically called the generator, it kind of takes the place of a policy. And I'm going to call it p theta, just like pi theta, only p theta. That network is going to do something a little strange. It's going to take in noise, random noise, and it's going to turn that noise into observations, into images, for example. So z is just some noise vector in Rn, x is, let's say, an image, and the network is trying to learn p theta of x given z. This looks a lot like the decoder in a VAE. So if you remember when we covered variational autoencoders, this is like the decoder in the variational autoencoder. So this generator, it's going to generate some samples. So you're going to sample random z's, run them through the generator, and you're going to get some sampled pictures. And then there's a data set. There's a collection of, let's say, images that are real images in the world, and those are going to take the place of our demonstrations. So instead of demonstrations, now we have data points. And we can think of those demonstrations as samples from some unknown target distribution p star. So in IRL, we had an expert generating demonstrations. Here we have an expert generating pictures. We don't know who that expert is, but we just see the pictures. And then we're going to train a second network, which we call a discriminator. And that second network is just a binary classifier. So it takes in images x, and it tries to predict what is the probability that this image is a real image. So it just outputs the probability of a Bernoulli random variable. And this classifier is trained as any other classifier would be. you get positives, real images, which come from your expert, and you get negatives, which are fake images that come from your generator. And the discriminator is just trying to maximize the log probability of the real data and minimize the log probability of the fake data. So it's trying to assign a label of 0 to the fake data and a label of 1 to the real data. And then the generator is going to go in and it's going to try to do the opposite. It's going to actually try to change its generation distribution to try to make its images look more real, to try to fool this guy into thinking that he's really generating real images. And structurally, this is very similar to what we saw in IRL. So in IRL, the policy will be maximizing the reward, while the reward would be trying to make the policy look bad. Here, the generator is maximizing the probability of being real, while the discriminator is trying to minimize its probability of being real. So you can actually make this connection quite formal, but let me go through the kind of how the pieces all line up, and then I'll describe the math a little more. So in generative adversarial networks, you train this discriminator P of real image given X. And if we know that the expert's distribution is given by pi star, or by P star, we of course don't really have access to P star, but if we did, and the generator is given by P theta, then you can actually show that the optimal choice for this discriminator would be the ratio of the probability. So if you actually knew P star, you could simply obtain the ideal discriminator in closed form just by choosing to output true based on the ratio of P star of X divided by P theta of X plus P star of X. This makes a lot of sense. Like if you have some X that has high probability under P star and low probability under P theta, then this ratio will be close to 1. If you have some X that has high probability under P theta and low probability under P star, then you'll have small number divided by big number plus small number, so it'll be close to 0. And of course, if you have some image that is just as likely to come from the data as it is to come from your generator, then this ratio will be 0.5, which means the discriminator is saying, I have no idea if it's real or not. And that means that you've won. That means that you've converged to the ideal distribution. Of course, we don't really have access to P star in reality, so we can't quite compute this. But if we could, then that's what we'd do. So what we're going to do for IRL is we're going to recognize actually that our P theta tau is given by is proportional to the product of the probability of a trajectory from the dynamics times the exponential reward. So what we can do is we can actually use this to parameterize our discriminator. We can actually plug in those quantities. So for pi star, we're going to plug in the product of the trajectory times the reward, and for P theta, we're going to plug in our policy. So remember that the policy and the distribution according to the model factorizes the product of CPDs. P tau here denotes basically the product of the initial state times the dynamics, which are the same for both the optimal policy with respect to the reward and for the expert. This is the exponential reward. Those are the optimality variables. And this is the product of the actions, which are the additional terms in the policy that you're sampling from. So of course, the p taus cancel out, and you end up with this very appealing ratio between just the normalized exponential rewards on both the top and bottom, and on the bottom you also have the probability of the product of the probabilities of the actions from your current policy. So if you represent the discriminator like this and optimize for R, meaning make a discriminator of this form be a good discriminator, then a convergence, this top thing has to be equal to pi star, because that's the only way that it can optimally discriminate. And these annoying dynamics terms canceled out on the top and bottom. So all we really have to do to use GANs to run IRL is we have to choose a very particular form for the discriminator, which is given by this ratio. And of course, these terms, the pi thetas, we have access to them, so we can calculate that product. So what we're going to do is we're going to optimize the discriminator to distinguish between demonstrations and samples, but we're going to optimize it for a discriminator of this form with respect to psi, which are the parameters of the rewards. So the psi that we're going to try to solve for is the argmax, just like with GANs, the argmax of the likelihood, which tries to distinguish demonstrations from samples. So it tries to assign high probability to expert data and high probability of being false to samples. And the only change, the discriminator now has a special form. And the reward actually lives inside the discriminator. It's a little bit more nuanced to prove this, so I'm going to state it without proving, but there's a paper reference that right here that contains the proof. You can actually prove that if you do this, then you don't actually have to calculate z. It actually turns out to be enough to optimize z with respect to the same objective. It's a little bit of a non-trivial result, but it's actually very convenient. So before, z was causing us a lot of trouble, and we had to use samples and importance sampling and so on to try to estimate it. It turns out that if we just train for this likelihood, we can train z with respect to the same objective instead of trying to estimate it as the integral of these exponential rewards. And if you want to see the proof of that, check out this paper by Chelsea Finn and Paul Cristiano. So that's actually very convenient. Now we don't have to estimate partition functions. We just optimize them with respect to the parameters, together with the parameters of our discriminator with respect to the likelihood of the discriminator. So now what does the resulting algorithm look like? Well, it basically looks identical to the guided cost learning algorithm I showed before. You have your generator / policy, and that's going to generate samples. You have your data or demonstrations from which you obtain some sample demonstrations. You're going to train psi with respect to this discriminator objective using the special form of the discriminator that has the exponential reward on the top and pi plus the exponential reward on the bottom. And then, just like before, you're going to train your policy to try to make the reward look big. And making the reward of the policy look big, of course, is exactly the thing that's going to fool this discriminator. So the algorithm that results from this at a high level is basically the same as guided cost learning, with the additional detail that you actually don't have to optimize you don't have to compute the importance weights, but instead you optimize the partition function z with respect to the same discrimination objective. And that can be quite convenient because those importance weights can become a little bit degenerate. So that's the procedure. It's essentially GANs for inverse RL. Does anyone have any questions about this? Okay. Now, why might we want to do inverse RL in these settings? Like, what can we actually do with the resulting reward function? Besides just imitating the expert behavior, one of the things we can do with the learned reward function is we can actually disentangle the kind of dynamics from the objective. So let me illustrate this. Let's say that you see some demonstrations for our favorite ant, which we all saw in homework 1, except that now the ant has some angry eyes, just for more character. And now let's say that we would like to imitate this behavior, but in a new setting, in a setting where 2 of the legs of the ant now are going to be disabled. So we want to reproduce the behavior under different conditions. So under this different condition, the actual gait that this robot has to execute is probably going to look quite different, but the basic objective is the same. So in both cases, they want to move to the right, but this one has to now turn around and use its remaining 2 legs to move. So if we want to do something like this, if we want to do this kind of transfer, then we have to figure out, like, what can we actually learn from the demonstration to enable better transfer? And I'm going to claim that actually the reward function is the right thing to transfer in this case. Because what you need to do is you need to decouple the goal of the task from the dynamics of the system, from all the stuff that's not under the agent's control. So which leg is operational or not is not under the agent's control, but the objective is. So if you were to directly try to imitate this with, let's say, behavior cloning, then you would try to move the legs in roughly the same way in this new setting, which wouldn't actually achieve the same goal. But if you figure out the goal and then re-optimize the goal in the new setting, then you can achieve good transfer. And the intuition here is that the policy is basically the consequence of your reward and your dynamics. In the Maxent framework, it's literally the product of the reward and the dynamics. So if you can tease those apart, then you can take your reward and put it in a new dynamical system and then re-optimize it and get a behavior that achieves the same goal, but potentially using very different actions. So that's why we might want to actually learn reward functions. But at the same time, we don't actually have to do this. So if we don't want to deal with transfer and we simply want to imitate the behavior in the original domain, we can actually take this GAN connection and we can simplify it even further. So we can have the same basic recipe where we have our generator or policy and we have our data. And now we're going to learn a discriminator, but we're not going to use that special form of the discriminator that has the ratio of rewards and policy probabilities. We're just going to do the regular thing and represent it with a regular binary classifier. And then the policy objective will be to maximize the log probability of the samples under the policy being like demonstration samples. So the policy is still trying to fool the discriminator. The discriminator is trying to classify, but it's not actually recovering a reward explicitly. It's just a standard binary classifier. And this will actually work. This will cause the policy to match the distribution in the data, because the only way that the policy can maximize log D, if D keeps adapting to it, is to visit the same states and actions as the expert did. This has some pros and cons. So if you follow this approach, which is called generative adversarial imitation learning, it was proposed in a paper by Jonathan Ho and Stefan Ehrman. The benefit of this is that it's often a bit simpler to optimize. It has fewer moving parts. There's no explicit reward function that we have to deal with. We just have this binary classifier. But it also has a few disadvantages. Because at convergence, the discriminator actually knows nothing about the task. So when does the system converge? It converges when the discriminator cannot distinguish demonstrations from samples. When the discriminator cannot distinguish demonstrations from samples, it's going to output 0.5 everywhere, right? Because 0.5 is the right thing to output if you're not sure if a trajectory is a demonstration or a sample. But of course, you can't take a discriminator that outputs 0.5 all the time and re-optimize it in a new domain, because your reward is just always 0.5. So this process really relies on the interaction between the policy and the discriminator to recover the behavior. And at convergence, the policy will approximate the expert's policy, but the discriminator will not actually provide you with an estimate of the expert's reward function. So if you want to just recover the policy, this method works very well. But if you want to recover the reward function, then you have to use the special form of the discriminator that I showed previously. So of course, what this implies is that you can't generally re-optimize log D in a new setting and hope for something to work. And in fact, if you have discrepancy between domains, then of course the trouble that you run into is that that discrepancy ends up being the most discriminable feature. So if I were to try to run this procedure where my policy acts in the domain on the right and my expert acted in the domain on the left, then the discriminator would simply try to guess, does this guy have 2 legs or 4? Which is not, of course, the goal of the task. It's simply the thing that distinguishes the 2 domains. So to summarize, in kind of the IRL view of things, you have attempts by the policy and the human demonstrations, and the reward function tries to make the reward be small for the policy and big for the expert. And this corresponds to learning the expert's trajectory distribution under the Maxent model. In generative adversarial imitation learning, there is no reward, there's actually just a classifier, and the classifier tries to predict true for the human demonstrations and false for the policy attempts. So the discriminator gives you the probability that tau is a demo, and you use log D as your reward function. And I should mention that, that both approaches have actually been used to achieve some really interesting results. This is some work from Carol Hausman and colleagues studying how generative adversarial imitation learning can be used to actually recover multiple different skills from heterogeneous demonstrations. So the idea here is that demonstrations contain different skills, and you would identify what the distinct skills are. And of course, these two things are at a very deep level actually the same thing, where the main distinction with IRL is that it just has a very particular form for the discriminator. Whereas for the generative adversarial imitation learning, it's just an arbitrary classifier. Here's another video to illustrate some results. This is actually with a variant of generative adversarial learning that is trying to imitate motion capture data of humans. So it's trying to learn policies that's trying to perform behaviors illustrated with mocap. So here, the expert demonstrations actually come from real humans, and then the resulting policies can learn some acrobatics, karate, and so on. And here's a comparison to behavior cloning, so you can see that by recovering the reward, you actually maintain long horizon stability and so on. So if you want to check that out, this is called the variational discriminator bottleneck. Okay, so to review, inverse reinforcement learning refers to inferring unknown reward functions from expert demonstrations. The Maxent inverse reinforcement learning is an instance of this where we infer the reward function under this model of approximate optimality based on the graphical model that we discussed on Wednesday. You can do Maxent IRL with dynamic programming in the case where you have tabular state and action spaces, and you can enumerate all the states and actions by simply, and then you can just sum together their visitation frequencies. And if you have high dimensional or continuous states and actions, and perhaps you want to not have access to the true dynamics, then you can use a sampling-based inverse RL, which generates samples to estimate the partition function and can also be interpreted as a variant of generative adversarial networks. So here I talked about the guided cost learning algorithm, connections to GANs, and so on. And of course also generative adversarial imitation learning, which is not IRL per se, but actually solves a similar problem. So you can think of it as basically just recovering the policy without recovering the full reward function. So if you want to learn more about these topics, here are some suggested readings. These are a couple of classic papers on inverse RL. This paper by Biela Ning, this discusses the maximum margin formulation if you want to learn more about that. And this is the original paper by Brian Ziebart that proposed the maximum entropy inverse RL formulation for tabular states and actions. And here are some more modern papers. This is the guided cost learning paper that I discussed. This paper by Marcus Wolfmeyer actually discusses a variant of the tabular maxent IRL algorithm, but still using deep neural networks as the reward function approximator. This is the generative adversarial imitation learning paper. And this paper proposes kind of a modernized version of IRL via that odds ratio discriminator. So if you want to learn more about these topics, I would highly recommend these readings. Okay, so that's it for today. And then I'll see you all next week when we start talking about exploration in reinforcement learning.